Hello everyone, my name is Ayush Matthew, and this is a summary of the paper, A Brief Introduction to NDN Dataset Synchronization, NDN Sync. The links for the paper are on the top left. Alright, let's get started. The paper was released in January 2019. It is continuing on the work of the original article, Named Data Networking, NDN. The main issue is how to reconcile the differences of a shared data set among multiple parties. We'll be mainly talking about how synchronization works on the NDN platform using two protocols the NDN has, ChronoSync and pSync. Before we begin, let's take a quick detour and refresh ourselves to the basics of named data networking. NDN revolutionizes today's host-centric network architecture, Internet Protocol, IP, to a more data-centric network architecture. Traditionally, clients' requests are routed to the website server and the packets are returned to the host, whereas NDN looks to solve the ever-increasing massive data usage from websites such as YouTube and Netflix. This method, they believe, will benefit both the consumers and the distributors. In NDN, when a consumer requests a resource by sending an interest packet, it is routed to an NDN router, and then the NDN router requests it from either another NDN router or the content producer itself. When they get the data back, they hold on to it for future inquiries by other consumers and then pass it off to the consumer that requested it originally. Now let's take a look at NDN packets. Included in the interest packets are the content name, various filters, and the lifetime of a packet. Subsequently, the data packet, which is returned to the router by the content producer and then routed to the sender, contains the content, meta information, and signature. And lastly, there is one more part to NDN, the intermediate step of receiving the interest packet and sending the data packets back to the consumers. So during the intermediate step, each NDN router maintains three data structures in order to carry out forwarding function: the pending interest table or PIT, forwarding information base or FIB, and the content store known as CS. When an interest packet is received, the router checks the CS if it has the data packets. If it does, it routes it back. If it doesn't, it forwards it to the PIT. PIT is where all the requests are stored, so when the data packets are received, it can be forwarded to the current consumer. The PIT forwards it to the FIB, and the FIB forwards it to the data producers. When the data is received, the PIT checks who asked for the resource, forwards it to them, and then the router also caches it into the content store. Before we proceed to sync protocol, let's quickly take a look at reliable multicast. The first type is sender-initiated protocol, where simply the data sender collects acknowledgements and performs retransmission of lost packets. In receiver-initiated protocol, each receiver is responsible for its own loss recovery, and it sends negative acknowledgements whenever it detects packet loss. Finally, asynchronous layered coding, or ACL. The ACL packets are transmitted through redundant coding so that the receivers can recover lost packets individually, minimizing the need for acknowledgements and negative acknowledgements. Each receiver can initiate a reception asynchronously. However, the redundant nature brings computational overhead and duly increases network bandwidth. Still doesn't solve the problem of retransmission. Now let's finally talk about NDN sync. What sync aims to do is reconcile the differences of a shared dataset among multiple parties, and the example we will use and used in the paper is a chat app. Users in the chat app will be part of the same sync group. Each chat message in the chat app is a named data unit, with the form being chat app prefix, chat group, and sequence number, with the sequence number always increasing. Each message is signed by the producer key, enabling a message of a named node to authenticate all received messages. Using sequence numbers allows others to deduct easily that they are out of sync. Thus, the naming convention can be simplified for all users in the chat room as producer prefix and then the sequence number. So, there are two sync protocols in the paper. First is ChronoSync and the other one is psync. ChronoSync synchronizes a shared dataset among a group of distributed users. Psync is designed to support partial data synchronization, which we will see later on. At a high level, both ChronoSync and psync adopt the same sequential naming convention, encode their dataset state, and periodically multicast sync interest to other users in the sync group. However, there are some differences, one of them being the data structures used for encoding dataset state and deducing the differences in dataset. The main goal of both sync protocols is to establish a stable state where all users in the sync group are up to date and there are no difference in local datasets. The sync process can be described as an exchange of sync interest and sync reply messages. If there are no new sync state differences, it will stay in the system and aggregate new requests by other users in the sync group to solicit future changes. There are three main components for ChronoSync and psync. First is the state representation, finding an efficient way to name a dataset, ensuring users maintain a local dataset, and then the sync state, where users can calculate their local dataset with other users in the sync group. Then we move on to state change detection, where users are made aware of changes in the shared dataset, either by data producers proactively notifying them, or each user periodically queries the sync group for any state changes. The final step is state difference identification. Each user in the sync group will compare their local dataset with the latest dataset and then retrieve the missing data. Now let's take a look at the basics of ChronoSync. It completely synchronizes a shared dataset among a distributed group of users. The goal is to achieve a stable stage. A chat group's dataset is represented by PI and sequence I, PI being the chat user's prefix and sequence being the sequence number of the user's latest chat message. And a state digest represents a hash value of each producer's latest dataset. A stable stage disruption can happen when a user is disconnected for a period of time, a user receives out of order delivery, or a state divergence happens when someone submits a new comment. A state digest is used for detecting state differences, and some of the differences it can detect are out of date, up to date, or the dataset is in a newer state. As for psync, it is designed to support partial dataset synchronization. Users can subscribe to a subset of data streams where they subscribe to a specific stream. IBF, or invertible Bloom filter, is an encoding dataset state algorithm which adds hash value of each data stream, latest data name to IBF, and it also uses XOR to identify any differences, as we see the example of squad A being turned into a hash. As for sync security, sync interests need to be authenticated to prevent injection of false information into the system for the signal dataset state changes. All parties with the same representation will generate the same HMAC value, which is a type of message authentication code involving a cryptographic hash function and a secret cryptographic key. The way to receive a key is through group management, where a single group manager or the leader is responsible for the generation and distribution and update of shared keys. When new key is generated, group manager can notify the sync group through key advertisement messages. The paper also discusses the challenges of NDN in continuous node movement and intermittent connectivity, where networking in mobile ad hoc environment or MANET is the norm. In this scenario, satellite, aircraft, and the HMMV act as an NDN packet forwarder. Losses are commonplace in MANET. Reconciliation is done by state digest or IBF. However, these are highly dynamic environments and they don't have much time for multiple rounds of packet exchange. Thus, there is a solution that the paper proposes for this. The solution being a state vector, as it couples state and data synchronization together. State vectors tolerate all degrees of state divergence. The node updates its state vector by taking the higher value of each producer's sequence number in the state vector, though they said this does have a lot of work to do ongoing. Although they have said there is a lot of work ongoing for this. Finally, in conclusion, the paper summarizes design features of existing NDN sync protocols, ChronoSync and pSync, and how these protocols reconcile a dataset among a distributed group of users. In terms of future work, the paper said the authors are looking into scalability and security as future challenges, using state vectors based design to support idempotent operation. And finally, for sync security, they're looking for a more robust solution to manage a group of shared keys. Thank you.